All right, let me do this question, and I think this is the last question I can cover at this session. So let me read the question. I chose this by the grouping of the questions, not I didn't actually read the question before selecting it. On some date, some guy or gal, I don't know if Udo is a man's name or some person, in Eastern Germany threw a shot at 22 meters. Oh, okay. So they're describing this kind of common projectile motion picture, like something with some velocity equals projectile motion. And I think the information they are giving us, that's the horizontal distance that it travels, because that's what they record, right? So some range is what they are telling us, and this is 8 kilogram or some mass thing. If the shot was released at a height, oh, okay, so I'm glad I drew it at some height. I guess it matters. And the projection angle of 45 degrees. Let me leave it as data. I don't know if it's always 45 degrees. Let me just leave it as data for now. It's asking what was its initial velocity. Okay, I guess this is a kinematics question, projectile motion question. So let me work through this, and I think this is one of those situations where you don't have a formula for, because it's not a level ground. There's an actual change of height that occurs. So for these questions, you really have to go back to your kinematics equations, which you can use this time because it's a constant acceleration, projectile motion, once it leaves the hand of the shot putter. So great. Let me write down the kinematics formula that I think I'll need to use. In the horizontal direction for projectile motion, it's really simple. Horizontal distance it travels, it's going to be, let me put my x initial equal to 0 here. That'll make things simpler. So the distance it travels is the horizontal component of the initial velocity times the amount of time. And usually you get the time information from the vertical component of the motion. So let me write those out. The y final is equal to, for projectile motion, your a equals minus g. It's going to be downward at g, so it's going to be minus 1/2 gt squared plus the y component of initial velocity times time, and I guess you do need the initial y height. Yeah? I think that's all I need. From this equation, I can get time, I can plug it in here, I can get r, and yeah. So let me add a couple additional pieces of information that comes from the setup of the question. So in the setup of the question, you basically know your final x position and the final y position. Final x position is r, the range that they gave us, 22 meters. And the final y position, where it lands, should be at 0. So I'm gonna make use of the fact that I know that information and write down that this is equal to r and that this is equal to 0. Good. This is what I recommend that you do whenever you are solving a new-ish type of physics problem-solving question where you are not given a kind of fixed set of steps follow, like a standard strategy, which we spend some time teaching. What I recommend that you do is after you've gathered your information, you feel like you have some handle on what's going on, do this before you engage in any serious algebra. 1, count your number of unknowns, and 2, count your number of equations. When you're done doing that, those two should exactly match. That's when you have exactly right amount of information to solve for the unknowns. So let me do that now. And it'll turn out that I have too many unknowns. So my initial x component of the velocity, I don't know. Mainly because I don't know the initial speed. So let me count this as one unknown. Time, I don't know. I have some sense of how I'm gonna get it, but kind of that's the part of the process. So time, I don't know. Second unknown. R, I know, it was given. G I know it's constant. T I already counted it, so I don't count it again. My Y component of velocity I don't know. So 3. Time already counted. My initial Y position. Oh, let me actually replace this with one of the letters I am using. So my initial Y position should be plus H. That's my initial Y position. So I have 3 unknowns, only 2 equations. So I need one more equation. And that one more equation will be basically the geometry of this. And when you are first learning to solve physics problems, it might take you more time to figure out where's my third equation, and that's the kind of the thing that you need to practice for. And what I'm giving you now is the structure for getting that practice, because once you see 2 equations, 3 unknowns, then you are looking for additional information. You shouldn't start solving this yet. So I think the easiest way to do this is so let me write down a bunch of things, some of which won't be all that helpful. So I could say, my V naught squared, use Pythagorean theorem. That's V naught x squared plus V naught y squared. Or I could say, I'm given angle theta that I haven't used yet. So I could say tangent theta is equal to V naught x over V naught y. And I think this comes with the practice, basically what's the most efficient way to get at some of the things that you need to get at. I think either of these equations are not all that immediately helpful. I think what's going to be more immediately helpful is basically expressing these components in terms of things that you want to get directly, V naught, and the things that the angle theta. So I can express V naught x as V naught cosine theta, and V naught here is technically a new unknown. So let me mark this as my 4th unknown. 4 unknowns, 3 equations. And finally, V naught y is equal to V naught sine theta. No new unknowns. So now I finally have 4 equations, 4 unknowns. Should be solvable. And I think this is a much more formal way of describing the structure of the information and the unknowns I have. So let me actually do this. It looks like these 2 are already kind of solved for the things I want anyway. So let me plug these into the equation so that I can just have 2 equations, 2 unknowns. And then I'll look at the question more carefully and see what I can do to answer the question. So plugging this into that, I have V naught cosine theta times time is equal to R. Let me call that my equation 1. And plugging this into that, I have minus 1/2 GT squared plus V naught sine theta T plus H is equal to 0. That's my equation 2. And many of you might have actually started with these equations, which is fine. That means you kind of know how to do this question. I'm laying out all these intermediate steps for people who maybe haven't had a lot of experience solving questions like this, and you find yourself getting stuck. The structure that I recommend to help you get unstuck is always do this. Split your question into 2 parts. The physics part, where you are trying to come up with the number of the equations that you need, and the second part, solving doing the math. And the check that you need to do to know when you are ready to move from part 1 to 2 is, does your number of equations match your number of unknowns? Here I have 2 equations. I have V naught and T as the 2 unknowns. And it looks like V naught is really the quantity that I care about. I don't care about T. So let me do this. I'm going to eliminate T. And once you've decided to eliminate a particular unknown, then the first thing you do is you solve for them. You solve for it in the most simplest equation that you have. And I think equation 1 is a simpler equation involving T. So let me do that. I'm going to solve this for T. That's gonna give me r divided by v naught cosine theta. And I'm gonna plug this in. So the reason I solve for t is so that I can eliminate it from all my other equations. So I can plug this in into equation 2. Everywhere I see t, it goes in. Then I end up with this minus 1/2 g and then t squared. So r squared over v naught squared cosine squared theta plus so some of the v naughts might cancel out. Let's see. I have v naught sine theta times t, again r over v naught cosine theta plus h is equal to 0. Good. Let me do some preliminary cancellation because I think so, you know, whenever I see squared things, it makes me worry that I might have to use quadratic formula, but I think here I might not have to. So this v naught cancels out that v naught, and this sine theta over cosine theta, I could simplify that as tangent theta. Let me leave it alone for now. And looking at where the v naught is, I only have v naught here, and everything else is a known quantity. So all I have to do is finish that algebra, isolate that v naught, and that's my answer there. Now, do I have enough room? I don't think I have enough room here. So let me do this. I'm gonna move some stuff. All right. So let me do that algebra. I'll this time I'll go step by step. I won't skip too many steps. So the first thing to do is I want to just put this by itself. And it looks like it has a negative sign, so the easiest thing to do is I can move this over to the other side, basically by adding this. Then, you know, it cancels out on the left hand side. On the right hand side, I'll have the positive version of that. Then I get this. Let me write out these two remaining terms on the left hand side. I get sine theta over cosine theta times r plus h is equal to, this thing moved over, 1/2 g r squared over v naught squared cosine squared theta. And the thing to do is move everything else that's not v naught over to the other side. And it comes down to doing a multiplication by a right factor. Here the right factor would be, just staring at it for a while, I think it's gonna be 2 cosine squared theta over gr squared. And what I'm doing here is I'm basically coming up with the right factor here to cancel out the 1/2, to cancel out the r squared, to cancel out the cosine squared, to cancel out g. That leaves me to just the v naught squared in the denominator. And as I do that, I have to remember to do this product on the left hand side to these two terms. So I guess let me do it this way. I'm just gonna group these within the parentheses and just multiply this. Then I'll end up with 2 cosine squared theta over gr squared multiplying to sine theta over cosine theta r plus h is equal to 1 over v naught squared. And let me do the rest in calculator. So I don't think this will really simplify all that elegantly. So it basically comes down to getting a numerical value for the what's on the left hand side, and then if I raise it to power of minus 1/2, minus for taking the reciprocal and 1/2 for getting rid of the square, then that'll give me the numerical value of v naught. So let me do that rest in the calculator, O from alpha. So I'll do 2 times cosine of the angle 45 degrees squared divided by g 9.8. Let me just keep everything in basic SI units, then I don't have to worry about units. 9.8 times r, 22 meters squared. And if you are not including units, make sure you don't make algebra mistakes. Sine theta over cosine theta, let me enter that as tangent of 45 degrees, which will be 1. Times r, 22 meters, plus h, 2.2. That's the 2.2 meters here. So that's the number on the left hand side. I take that whole thing raised to power of minus 1/2. That gives me 14. I'm pretty sure that's how the question was generated. It probably generated the speed first and then did the rest backward. Let's just double check. Good. Then now, if while in Bayer's hand, the shot was accelerated uniformly over a distance of that, what was the net force on it? So I still have to do a little bit of kinematics and looking at the question, uniform acceleration. I don't care about the time information. I have a kind of a difference in velocity, final velocity and the initial velocity was 0. It's all the situation that makes me think I want to use the V squared formula. V final squared is equal to V initial squared plus 2 times A times delta X. Once I get A from here, I can multiply it by the mass of the shot to get average force. So let me solve for this for acceleration. Acceleration is, this algebra I'll just do in my head. V final, which will be V naught there, so V naught squared minus the V initial squared, which will be 0, divided by 2 times delta X. I'm given the delta X here. 2 times delta X, and then I take this, multiply it by mass to get me the force. And I think I can do that also in the calculator. So so I have this number, which is my V naught. So I'm gonna take that squared. I know I can do it by changing some of these numbers, but let me do it this way. I'm not gonna subtract by 0. I'm not gonna write it down. Divide by 2 times delta X in basic SI units, 1.2 meters, and then times the mass, 8 kilogram. So this tells me 653. Let me see that if that gets graded. That should get graded as correct, I think, even if the thing requires 0.1% precision. Yeah. So, so that's the answer. So this was a more of a kinematics question than a force question, because once you knew the kinematics parameters of it, then the force part was pretty easy.